So, as you can read, the title is Neural Parametric Singing Synthesizer Modeling Timbre and Expression from Natural Songs. So it means that we want to learn from actual natural singing. We want to learn style-related expressions. We want to learn timbre variations and using convolutional networks. So I'd like first to start with a bit of motivation of my background and why we are doing this. I forgot to mention that this work has been performed in collaboration with Marlijn Blauw, my colleague at the MTG. So, well, singing voice is, someone might say that it's probably the most complex instrument to imitate and to synthesize, and almost everybody sings, at least in private. And you know that synthesizers have achieved a very significant realism for many instruments, using sample-based synthesis or modeling strategies or performance sampling. But for the case of singing, we could argue that it's still a bit far from getting a transparent quality. But on the other hand, it's already good enough for music production, especially in the case where we don't pretend it to be realistic. So this links with all the avatar stuff, where you have a machine singing, not a human. As Axel mentioned, we started collaborating with Yamaha 20 years ago, and since then we've been doing research in voice processing, especially in singing. But actually we started building what was a real-time morphing for a karaoke, so we wanted an amateur singer get into the karaoke, start singing, and then the voice getting transformed in real time and sound like a professional singer. However, this failed commercially, and the main reason was that for each song we wanted to perform in the karaoke, we needed to record that song by the target singer. So if you want to the karaoke, you want to sing any song as your idol, which you don't know a priori, so that's impossible. So then, what we did was, we thought it's more interesting to take one singer, record several hours, whatever we need, and build a model which is able to sing any song. And that's the singing synthesizer, and that was the beginning of Vocaloid idea. So Vocaloid is the most successful commercial singing synthesizer nowadays. It's by Yamaha, and we've been developing that in collaboration. It's very popular in Japan, but essentially how it works is very simple. So it has an interface which is similar to a MIDI sequencer. There's a piano roll. You can input the notes, the lyrics, some expression controls. And it seems easy to use, but actually it's not, because if you want to generate really expressive performance, you need a long work. It's hard to generate, and users need to learn, develop their own skills, and users' experience is really relevant. A bit of history, it has been changing over the years. We started, that's the first sound generated using sinusoidal plus residual models. That's Japanese. And there was the presentation of Vocaloid in 2003, some choir. And then the product came out. But it was aiming at a professional audience, so to be used in post-production studios where they want to have a very, very good sound. And it was, well, when they announced it, the statement was like, you have a slave singer in the recording studio 24 hours a day, 7 days a week. And it didn't sound like what one might expect. That's a Miriam voice. So quite far from being really realistic. It didn't get popular. But then in 2007, something happened, because the second version, we changed the processing methods to something similar to phase vocoder called spectral peak scaling. And it really became very popular. But we'll explain why. Let's listen one example of Vocally 2. So the voice is still not really realistic, but the music is very different, the audience it targets is very different, and we'll see something more about this later. But just to get some insights of a more recent example, having some unit selection approach using similar technology.
It's coming down the track, Jack. Come on, let's get on board. Well, ding dong, ding. Listen for that A train. You find.
So the quality is improving, but the question is why it became so popular at the time in 2007. And one might say that maybe it's because you can obtain realistic results if you use it in a performance-driven way, so you provide human control. But that's not the reason, because that was not available to end users at all. So they had one process. Also, in terms of the synthesis quality, it did not excel in academic contests in which Vocaloid participated. For example, in 2007, there was a singing challenge. And the technology itself was not that much different from what was used for diphthong synthesizer in speech, for example. So why? And the reason is really the strong link to the Japanese anime culture, to the avatars, the manga, and internet communities, but also having a company which can spend money in creating databases and segmenting manually and so on. And also the community phenomena around that was really huge and implied someone was composing something. That was the time where Facebook and Google started becoming very popular. There was the YouTube also, and Nico Nico Doga, which is the Japanese version of it, so somehow. And then people start dressing like the avatars, and one composes, the other makes the video, etc. So, but then still there were a lot of limitations. So what was coming next? And we could say that after my experience with it, the most significant limitations, we could say, are the poor default expression. So you need to spend a lot of work in order to produce something really expressive. And we have been doing some stuff, some research trying to get some style modeling using context-dependent HMM models, unit selection for control, expressive control, lately autoregressive convolutional networks. Another limitation is the effort required to create a voice. So it can take months to create a database for English voice, for example. And for that, we've been doing some research on singer conversion, even with the idea of resurrecting dead singers, or automatic voice creation, with the idea of having a system which is less, depends less on the segmentation errors. And also, model voice quality is very important, because if you put together all the voices, 100 voices that are in Vocaloid, in the end, all of them sound very similar. So there is a lack of uniqueness in each of the voices. So, and for that, it's needed to do some voice quality modifications, like voice source modeling, or through morphing with expressive samples, or learning from data, again with convolutional networks. So in this talk, that's the motivation. I want to focus on our latest efforts using convolutional networks. And the goal, again, is to model the voice and the singing style of a specific singer from natural songs. And you know the state of the art. We have the Foreman synthesizer, physical models, concatenative methods, which have good quality, but cannot jointly, or it's difficult to jointly sample together musical and phonetic context from a single data set. Then we have the machine learning approaches, like HMM, which have a lower sound quality, but are able to jointly model timbre expression and also are much more flexible. They can deal with multiple speakers. There is some transfer learning, model adaptation using just a small training data, etc. And recently, 1 year ago, there was, especially to me, it was amazing what was done with WaveNet in the sense that it really improved the sound quality predicting raw waveform using convolutional networks with very simple conditioning, just current phoneme, previous phoneme, next phoneme identity. And I thought we could try that with singing, the WaveNet approach, but WaveNet is modeling raw waveform, and for singing, okay, WaveNet requires large amounts of data. Typically, they use several hours, tens of hours of data. It's used for speech. And in singing, we have a much higher pitch range and also much higher timbre variations. So it's quite difficult for singing. So what we thought is, let's use a similar approach, but instead of predicting raw samples, predict vocoder features. And that's what we did. So we base our model on the WaveNet model. We have some modifications over it, but we model vocoder features. And one reason is because with vocoder features, we can somehow separate the influence of pitch and timbre, or have them model them separately. So less training data is needed for covering the timbre pitch space. And we know that the vocoder is degrading sound quality, but still we believe that the degradation, the most important degradation is produced by the model itself, not by the vocoder. So that our top ceiling is the analysis for synthesis obtained with the vocoder, and with an autoregressive model such this, we ideally should be able to get such quality. So this is an overview of the system we have built. And as you can see, it's separated into the top there is the training phase, in the bottom the generation phase. And we have three main blocks, which is one, each of these is a neural network. So one network predicts phonetic timings, another network predicts pitch, another network predicts the timbre, sorry. For training this system, we use songs. So like 30 minutes, 30 songs, something like that. We'll see later. And those songs are phonetically transcribed and automatically segmented. We cut them in sentences, and then we apply a segmenter, a deterministic annealing segmenter. Apart from that, phonetic segmentation, then we use the notes from the musical score. We don't change them, so we just transcribe the notes from musical score and the corresponding segmentation. And we extract acoustic features, in our case, using the Whirl vocoder. Then, when we want to generate, the first thing we do is we use the musical score and phonetic sequence. We don't know the phonetic durations at synthesis. We only know the phonemes tied to each of the notes. So this first model predicts phonetic timings. The second model uses the musical score and phonetic timings to predict F0. And the third component uses phonetic timings F0 and predicts the acoustic features, which in our case are the harmonic spectral envelope, aperiodicity envelope, and the voiced-unvoiced decision. And the last part is to feed the acoustic features and F0 to the synthesis part of the vocoder to generate the audio. So, as I said, we are using an autoregressive probabilistic model. And we could say that the basic idea of this type of models is that we formulate the joint probability over the whole utterance as the product of the conditional probabilities for each time step with a causal ordering. And the model predicts conditional probability distributions. and what that is to maximize the likelihood of the future information given the past observation and the control inputs. At synthesis, predictions are obtained by sampling the conditional distributions in a sequential manner, so step by step. We predict one sample, that sample is fed as input, past sample, we shift one step, and so on. And in our case, we predict multivariate vectors, which correspond to the acoustic features of a single frame. That's different than what is done in WaveNet or Pixel CNN or Pixel RNN, because they predict univariate variables. So they predict each of the channels of the RGB channels of a picture, or predict one sample. And we also consider, in our case, the variables within a frame, so the acoustic features to be conditionally independent. So, but note that they depend on, in past samples, they depend on all other features, not in current frame at each frame, but yes, there is some dependency considering the past. This is the modified architecture that we used. And as you see, that's for the timbre prediction. The input are acoustic features. The outputs are conditional distributions, so the probability distribution of each of the features. And the control, in our case, corresponds to a very simple set of linguistic features, which are the previous phoneme, current phoneme, next phoneme, and the normalized position in the current phoneme. Then the network itself consists of an initial causal convolution. It has to be causal because we cannot use future information. So we have a set of past acoustic features, then there's this convolution, and then a set of layers. And then for each layer, they have a dilated convolution, a gated unit, combining sigmoid and 10H nonlinear activations. The control features are added before the gated unit, and then there is a residual connection and skip connections. In the output, the skip connections of all layers are added together. Then there is a non-linearity gain, and then we have another convolution to get the outputs distributions. Another different from WaveNet approach, they predict samples and they don't assume any specific shape for the distribution. So in WaveNet, there is a 256, because they use an 8-bit compression, 256 softmax as the output layer. But in our case, this becomes overwhelming, too much weights, and it gets too big because we are predicting many features at the same time. And if for each feature we have to have a softmax of 256 and we have 60 features, for example, that can be too big. So instead what we do is to constrain the conditional probabilities to a certain shapes, which are mono mode. So we don't allow multiple modes in the probabilities. And we don't allow very small variances. And we use a mixture of four Gaussians, but with some constraints, so that we offer three parameters, which are location, it's kind of the mean of the distribution, the scale, kind of the variance, then the skewness. For example, here skewness, it's an asymmetry towards the left, and then the shape, which can be more like a hat than like a Gaussian distribution. When we first try this approach and generate our synthesis, we find out that the models were not really following the control. So they more or less sing what we ask to sing, the lyrics we ask, but sometimes they really use arbitrarily different lyrics. And one reason is that well, the reason basically is that the model often relies too much on past inputs instead of on the control inputs. So it depends too much on the past acoustic features and not so much on the control inputs where we tell the system what we want in the future. So, and one reason for that is that errors that happens at generation are some propagated at future time steps. And they kind of compound and change the acoustic features, and since the model relies on acoustic features more than on control, then it derives to a different path. So in order to improve that, we proposed a simple regularization, which is just adding Gaussian corruption noise to the input acoustic features. So then the model has two inputs, has acoustic features with Gaussian noise and has control inputs which are clean. So then the model relies more on the control input. That's the idea. However, one side effect of that is that the output distributions become more noisy. So the scale or the width, the variance becomes wider. And, but that can be alleviated by a temperature control on the distribution. So basically it's to produce more narrower distribution. We tried other regularization techniques such as dropout, but we did not find them to be better than just injecting noise to the input. So now I will talk a bit about more detail about each of the models. So let's start with the Tammer model. And we use, we have to predict three types of features, which are the harmonic features, the periodic, and voice-to-voice. And we use a multi-stream approach. So we have three independent networks, which are trained together. So each own has a loss function, a loss objective, and all the losses are added together, and the training is a single one. However, at synthesis, we can use the output of one of each. For example, we use the output of the harmonic, the predicted value, and we input that to the aperiodic model, and the output of the aperiodic and the output of the harmonic are fed, of the current frame, I mean, the current time step, are fed to the voice-to-voice decision also. Then, for generating the pitch model, well, we know it's quite challenging to generate pitch contours because there are many aspects that affect it, like we have a musical at different scales, we have the melody, phrasing, vibratos, etc. We have phonetic microprosody, we have the motion or the meaning of the word. And some approaches try to decompose the F0 contour into different layers, for example, separating vibratos, or even use, well, we actually have used for, in other research, material without consonants to get rid of the microprosody. But in this case, we model F0 contour as it is, so we don't apply any decomposition, and we just fed that as the observations that we want to learn and predict. We use the modified WaveNet architecture that we showed before. But we found that in the datasets we use, like 30 songs, we are not sufficiently covering the musical and phonetic context. So we perform some data augmentation on the data set. And for that, we make two assumptions. The first, which might be not true, probably, is that the pitch gestures are largely independent of the absolute pitch of the notes. So that if you transpose the melody, you will, the singer can produce the same contour and sound natural and realistic. That's one assumption. And the other is that the microprosody is mostly dependent on phoneme class. So not on the actual phoneme, but for example, if we have voice fricative, that all voice fricative will behave similarly. That's another assumption we do. So we perform the data augmentation by randomly pitch shifting the training data. So we just a constant pitch added to each of the samples in the mini batch during the training process. And also we randomly replace the phonemes by others of the same phoneme class. So that means that what the model is training are nonsense lyrics, because we are replacing randomly vowels by vowels and voice fricative by voice fricative, plosive by plosive, etc. Actually, one straightforward improvement to that would be to just input not phonemes but phoneme classes. But we still have not done that. But probably we arrive to the same results. We did that, but we also found that usually or often the model could produce perceptually out of tune singing. And so we applied some moderate post-processing, which in this case it's quite robust and straightforward because we know the note segmentation. So we know the notes, and we have some pitch contour, so it's easier to perform tuning. And one reason for that is that, well, we inspect a bit the data set, the recordings, and we found that just plotting the nominal score and the singing pitch contour, we know that there were several notes where there were significant pitch deviations, but perceptually they didn't sound out of tune. So sometimes it depends on the musical context. Rapid notes, for example, tend to be more out of tune than long notes, etc. And finally, the last is the timing model. So we need to predict phonetic timings, and we use a multi-step prediction. So we have one network. The first is to predict note deviations from the nominal score, and it's a simple feed-forward neural network where the output is non-parametric conditional probability using a softmax, and it's each of the bins of the probability is correspond to multiples of the hop time. Then we have the phoneme duration model, in this case a convolutional network, which is non-causal, because we can use the future information, phonetic information. It also uses the notes information. And also the output is a non-parametric conditional probability, where each of the bins is a log scale of the duration. And finally, we take the predicted durations for all the phonemes for each note, and we perform a simple fitting heuristics, where we basically expand or shrink the vowel. We consider some threshold, relative threshold of duration, minimum duration for the vowel, and shrink consonants only if needed. The acoustic and linguistic front end that we use is, as I said before, the world vocoder. We have a 5 milliseconds hop time, and we synthesize at 32 kilohertz sampling rate, and we use a reduced dimensionality of features, so 60 dimensions for the mel frequency spectral coefficients, and 4 dimensions for the band periodicity. Here in this table you can see the inputs and control inputs and feature dimensionality of each of the networks. This is the one for predicting timbre. So control inputs are the phonetic information, previous, current, next, position, and F0. Then for the F0 prediction, the F0 control prediction, we use the some phonetic information, phonetic position in the current phoneme, some note pitch information, note duration information, and the positioning node. It's important to notice that since we're using convolutional networks, actually, even though we are only informing the system about the previous node, but since there is a receptive field of the network, so to predict one sample, it uses several past samples. Each of these past samples has its own control input, so it has more information than, in the end, more information than the previous phoneme, so it might be several phonemes. It depends on the receptive field of how long it is, of how many phonemes or notes actually control, affected. And then we have also the same information for note timing and for phoneme duration. Maybe we skip some of the details. And finally, for generating the synthesis, these models, autoregressive, tend to be very slow because we have to work sample by sample. We cannot parallelize it. So anyway, compared to predicting raw waveform, there's a clear advantage, much lower sample rate. Here we have a 200 hertz, 5 milliseconds, versus 32 samples per second prediction. We have much fewer layers covering a similar receptive field around 100 milliseconds, for example. So 5 layers versus 30 for WaveNet, or 1 million parameters versus 50. Weights, sorry, parameters of the model, I mean. We implemented in CPU in C++ an algorithm for synthesizing, and with that we can generate speeds for predicting vocoder features between 10-20 times real time, so it's pretty fast. And also the memory footprint is also important, so we don't have a data set, but we just have the model parameters, so it's less than 5 megabytes. So it's fast, and memory footprint is very small. Of course, we performed several experiments for evaluating the performance of this proposed system. And we had 2 objectives in mind. One was compare it against competing systems, against unit selection, HMM, and DNN. And also, we want to get an indication of the absolute performance. So how does it compare to a recording? And we have used rather small data sets, especially compared to ones typically used in WaveNet for training speech. And basically, we use a natural singing dataset, which is publicly provided by Nagoya Institute of Technology. This is the one that comes with the HTS Toolkit demo. And there is a female singer singing Japanese children's songs. And the public available part consists of 31 songs, although the complete data set is more than 70 songs. Those are kept private. And we use 28 songs for training and 3 for testing when we train the network. Apart from that, we also have another data set, which consists of pseudo singing. Oh, let's play one how it sounds natural singing, one of the samples. And then we have pseudo singing, which sounds like this.
I wish someone could cure this pain.
So this is singing at flat pitch, at constant cadence. And that's good for concatenative synthesizer, for example. And in Vocalith, that's a typical approach used to build data sets. And we had access to 3 proprietary data sets, 1 English male, 1 English female, and 1 Spanish female also. And for Spanish, for each of the pitches, several pitches were recorded, 3 pitches, and for each of the pitches we were using over 100 sentences for Spanish, much more for English, because English is phonetically much more complicated. And we randomly select 10% of sentences for testing. So the system we have compared are the NPSS, is the one we proposed, Neuroparametric Singing Synthesizer. Then we have the IS16, it's the concatenative unit selection that we presented last year at InterSpeech. Then we also compared to the publicly available implementations of SYNC. There's one based on HMM and another based on feed-forward DNN. And also we implemented an HMM based singing synthesizer on the HTS toolkit. And for evaluating the experiments, we use several quantitative metrics and perform listening tests. For quantitative metrics, we use compute the Mel-Kapsel distortions of a harmonic component, the Vanna periodicity distortion of a periodic component, the modulation spectrum, which is especially important here because it's estimating the variance over time of each of the features. A modulation spectrum, actually the log spectral distance to get a single value. The false positive rate and false negative rate of voiced and voiced. Some errors for timing and F0. And modulation spectrum also for log F0. And for listening test, the mean opinion score and preference test. So, some of the quantitative results. This is for the timbre model trained on natural singing. So on top we can see, in terms of Mel capsule distortion, MPSS is on par with DNN, and it's better than HMM and unit selection. Clearly performs better in terms of modulation spectrum. Actually, here we can see the modulation spectrum of second Mel generalized coefficient and 6 Mel generalized coefficient. In blue is the natural singing, which has a lot of much high frequencies. And then in red we have the MPSS. Then for aperiodic, the distortion, it's also better with MPSS. But for voiced-unvoiced, it's rather unfair or worse. Here there is a very nice plot where we compare the F0 contour generated of a short excerpt with, in blue we have the natural singing, the MPSS in red, and then we have in this in orange and green HMM and DNN. You can see that HMM and DNN, actually the vibrato, it's almost the same, only differs in some depth. So that makes us think that actually in the DNN approach they are not doing anything special, but they are just reusing the HMM prediction because it's identical. But it's very interesting that the MPSS predicts a varying vibrato rate, so it's not rigid, it's not constant a long time, and that's also true for the natural singing. It's not constant, but there are some variation. And for example, at the beginning, it's a bit slower. But also more important than that is that using in SYNC HMM or DNN, we are looking to some acoustic feature which is rather flat during the vibrato. That means that but if you observe natural singing, we see some synchronization of this acoustic feature with the vibrato in natural singing in blue, but also MPSS is capable of producing such synchronization between timbre and vibrato. And the reason is because MPSS is conditioned on pitch, on past pitch samples. But in SYNC HMM and DNN approaches, they are only conditioned on the note pitch, which is flat over the note. So they don't know anything about the vibrato. And that makes a huge difference in terms of perception. Regarding the timing quantitative results, we can see that overall, comparing MPSS with HMM approach, it gets better results. The only metric where it gets worse is for the root mean square error of note offset deviations. And for F0 quantitative results, we have the modulation spectrum, where it gets better, again, MPSS compared to HMM or DNN approaches. Here we can see the plot of the modulation spectrum of log F0. And it's noticeable that, for example, if we look at the vibrato range, which would be around between 4 8 hertz, that there is a very prominent peak for HMM and DNN SYNC. And that's because they basically predict vibrato rate of 5 hertz. We don't observe such behavior in the natural singing, where the energy is much higher, and also in the MPSS. So it predicts a different vibrato rate. Then when we focus on pseudo singing, all the previous results were for natural singing, but on pseudo singing, we found that that it's quite disparate in voice than voice. Sometimes one gets better than the other. For aperiodic, NPSS is significantly better. Also for modulation spectrum, in all our tests, modulation spectrum excels, but it's worse in capsule distortion. So then, one question is, okay, we have several quantitative metrics, but what does it mean for listeners? So it really reflects the perception, and actually, when we look at the results of this is the mean opinion score, we see that MPSS is much higher rated than SYNC HMM DNN or the concatenative synthesizer, which is the worst in this case. It's rated the worst. So there is a huge difference in terms of perception. Not so much in terms of metrics. In metrics, in the objective metrics, basically there is a very clear improvement in modulation spectrum. And also in preference test, AB, both a cappella or mix, there is a clear preference of the MPS system against HTS or the concatenative synthesizer trained on cellular singing. So in both natural singing and cellular singing. We can listen one of the examples played in this evaluation. So we have the reference. The unit concatenation. It really suffers, the unit concatenation here, because we are using natural singing, including vibratos in the data set. And when vibratos, and especially in kind of lyrical singing, vibratos are prominent and deep, it's very hard for unit selection concatenation systems to change the pitch and don't distort the timbre in a nice way. So it really suffers. Then the HMM. DNN. MPSS. Also, it's important to mention that both SYNC HMM and DNN are using the whole data set of 70 songs, which are not publicly available. And for MPSS, we are using just the 30 available data set. And for this experiment, we use songs of the validation. We're using as a control, scores from, in our case, the validation, but they belong to the training data set for HMM and DNN. So some more examples. Okay, first, a Spanish female singer trained with 3 pitches of pseudo singing. This example is performance driven, so it means that the input for synthesizing is phonetic durations and F0. And the rest is predicted by the model. So then we did an experiment where we added to the training. So we have a data set of 3 pitches, sentences sung at pseudo singing, and then we added 4 minutes of soft singing songs. And we trained that together, and we conditioned the system saying this is soft, this is modal. And then at synthesis, we could ask for singing anything soft or anything modal. So in this example, it's excerpt of the previous, the same song, but it's generating several unseen phonetic contexts in soft quality.
Siempre serás bienvenido a este lugar, a mi lista de obsesiones que no vas a olvidar. Cómo recordarte sin mirar atrás. Yo nunca olvidaré el último vals.
And then we tried something similar with power, voice quality. But in this case, we have the recording scripts, but we use just half the recording script set for low and mid pitch. And then we ask at synthesis to generate the higher pitch range because it's the part of the song where it goes higher. So it's generating unseen high pitch powers.
Siempre serás bienvenido a este lugar, a mi lista de obsesiones que no vas a olvidar. Cómo recordarte sin mirar atrás. Yo nunca olvidaré el último vals.
Okay. Then we have another example, in this case, not pseudo singing data set, but natural songs with a NITEC data set of Japanese children's songs. First, short excerpt, which is performance driven, so phonetic durations and F0 are fed to the model.
うさぎ追い鹿の山こぶなつり鹿の川夢は今も巡りて
Okay. And then another example where we use the full system, so we predict no deviations, phonetic timings, F0, and timbre, so out of the score, using the same data set.
空を押し上げて手を伸ばす君の夏の音どうか来てほしい水岩まで来てほしいつぼみをあげよう岩の花水木娘に世の乾い霧のね果てない夢がちゃんと終わりますように君とせないのが100年続きますように
Okay, and last example. It's we did experiment to generate a choir. So we trained with a single model. We recorded 3 singers per section, so 3 bass, 3 tenor, 3 alto, 3 soprano. All of them singing, pseudo singing, low, mid, high pitch. of their own register. And we condition during training the network by the singer identity, so just telling it's singer A, singer B, singer C. So then we have a single model. All weights are shared, and only in the conditioning is what selects which is the singer we want to listen it in the output. And the memory footprint is 4.3 megabytes. And this example is one traditional Catalan song, Rossinyol, and you will listen this part. It's performance driven in this case, so we still have not, we have to deal with the interference or how they synchronize singers, etc. So we're not dealing with that at this point. But we took one singer per section and we asked to sing his part 3 times. And then we use each of those as control, so phonetic durations and F0 to control it. So, final words. Summary, we have presented singing synthesizer based on neural network on a modified WaveNet architecture, which can generate singing from musical score with lyrics. And we have separate but interconnected models, which can predict timbre, pitch, and phonetic durations and note deviations from data set of songs of natural singing. And as conclusions, we believe that this system notably improved the quality compared to previous HMM approach, to conventional HMM. And it doesn't depend so much on the perfect phonetic segmentation as unit selection approaches. So it can allow some deviations. And it has many practical applications, and in part is due to the fast synthesis and the small footprint. And it's also a very flexible approach, and we believe there are many future directions that we should work on, like modeling jointly, timbre expression, where we are actually doing, sorry. But we can improve that and add more voice qualities, for example, add growls or different voice qualities to the expression modeling, multi-singer training, like this example we saw, model adaptation, etc. And, well, what's the vision for next years? We believe that the significant increase of naturalness and ease of using singing synthesis is coming. Not only for this, but for also the work you are doing here. So thank you very much.
Thanks, Jordi. Are there any questions?
Thank you very much for your presentation. It's very impressive, and congratulations. I have just a little questions about one thing. If I understood well, you use machine learning to output features for the vocoder, right?
Yes.
Yes, okay.
To predict features from the vocoder, yes.
Okay,
Yes.
but do you backpropagate on the features or at the output signals?
So the network, this is the output of all the models. So basically, what we predict in the end is vocoder features. So we predict the periodicity number at each time step, and that's set to the vocoder synthesis. Then the predicted features are connected to the input, because this is advancing step by step, predicting one observation, then that observation goes to the class. Predicts one observation and advances step by step.
Okay.
Yes.
Thierry?
Jordi, so to be sure that I understand correctly, what do you mean by pseudo tonal database? Is it a human speaker, a human singer singing?
Pseudo singing, it's like I am singing like this.
You're a human person, and
Yes,
then
a human
and then you
person.
modified the pitch artificially.
Yeah, let's say from this recording, we analyze it with vocoder. We train these vocoder features, acoustic features,
Okay.
and those are trained and modeled by the network, which predicts vocoder features, and then synthesized again.
Okay. But at
So,
some-
there is no units of the data set which are transformed, but the model out of the control inputs predicts the probability of each of the features, of the acoustic features.
Okay. And when you say in just the previous slides?
Yes.
Yeah. Okay, again? No, sorry.
Later?
To the end, a bit more.
Okay,
Yeah,
sorry.
okay, there.
Yes.
You say, okay, when you say trained with low, mid, high pitch model, so
Yes.
that means? Just
That
to-
means a low pitch group of sentences which are pseudo singing.
Natural?
Yes.
Natural human singing? Okay.
Natural singing,
Okay.
mid pitch and high pitch
All
to
natural.
cover the risk.
Okay.
All natural. Yeah, everything
Okay.
is recording. Everything is learned from recordings of people singing.
Okay, and so the network learns itself how to change pitch
Yes.
in between these pitch values.
Yes.
Of course. Okay.
Yes. In the case of the first case of pseudo singing, so we have like 3 pitches.
Okay.
So then, when we train the network, we tell, because in training it combines randomly some part of the low pitch, mid pitch, and high pitch together
Okay.
for each update on the network.
Okay.
So then, we tell the system, when training, we tell that this is low pitch or mid pitch or
Of
high
course,
pitch.
yeah.
We identify with some number, with
Okay.
a hot encoding, one hot encoding. So it's 100, it's low pitch, 010, it's mid pitch, and
Okay. So
01
the
is
system
high pitch.
knows which database it's using,
Yes, exactly. It knows which
Okay.
pitch is.
and then when you generate,
You tell you have to.
you have to
input
say which
pitch.
Okay.
Yeah.
Aha. Okay.
And for doing that, so if you have the continuous pitch contour, so then you encode it from.
I see,
You have
okay.
the reference pitch of low pitch, mid
I
pitch, and
see,
high
I see,
pitch,
I
and
see,
you
I see.
encode it
Okay.
in coarse encoding,
I see.
like 100 or half if it's in between, and so on.
Just because it's the same direction, that means the network does not learn to synthesize intermediate pitches.
No, in
Because
training
you
with
force it to
exactly,
always-
exactly. But that's for the case of pseudo singing. For case of natural singing, it does because the pitch is continuous.
Yeah.
Yeah, and from our experience, it's better in terms of the timbre produced, and also for the singers, it's much nicer.
But I mean, if it's using natural singing, that means it does not interpolate something new because it has seen all these things.
Yes, but it has not seen all phoneme
Yeah, sure.
context in all
Yeah.
pitch context. It has seen
Did you
some-
try with the first thing? What would happen if you would synthesize or control it with intermediate values? Would it fail completely, or would there be something intermediate that would be sound
at synthesis?
at synthesis, just using the natural pitch to control?
But that's this example. The above example, it's we at synthesis we input performance ribbon. We give the pitch obtained from analyzing a singer.
Yeah, but then, as you just explained,
Yes.
then for the synthesis, you quantize the pitch to go
Yeah.
into these classes.
No, it's a coarse quantization. So if it's between the first and the second, instead of 1, 0, it can be 0.8, 0.2. So we tell the position, we interpolate. In the conditioning in training, it's always 1, 0, 0 or 0, 1, 0. But at synthesis, not. At synthesis, you ask for something in between, so you can say 0, 3, 0, 7, 0, or
Okay.
anything.
I see. Thanks.
One microphone, but 2 questions.
Okay, go on.
The first one is performance-driven. What
Yes.
is it exactly? It means that you predict F0 on durations?
No, performance-driven means that you take a performance of a singer,
Yeah.
you record him or her, you analyze F0 and segment phonetically, and that is the control of the synthesis. So basically it means that when it's performance driven, we only use this file.
Okay, only timbre. Okay, so, right. And second question: what to do with voice registers? For example, with falsetto or modal voice. And when in a song,
if it happens in the natural singing, the system learns that.
Okay.
You don't need to tell. If it's something systematic, I mean, if it's something that given a musical context or above certain pitch, for example, you change the register, it will learn that.
Change the timbre.
Yeah.
Okay.
Exactly.
Thanks.
Impressive synthesis. Thank you very much. I'm wondering how it is related to the training database. How much is it related to the training database? Because in your sound examples, you showed that if you modify the training database, for instance, if you take a shorter training database with only selected items, it changes significantly even the timbre, the way it sings.
You mean the soft or power example?
Yeah. So I was wondering how much this kind of synthesis is dependent and influenced by the training database.
It's totally influenced by the training database because it basically learns features from a database. So, but in this case, let me explain again what we do. So we have a data set of modal singing, and we have 3 pitches of a set of sentences recorded in stellar singing. Okay, that's our model database, and that's how we generate a buff example. But then we add to this data set another data set, which is just 4 minutes of soft singing songs. So we have together the model data, model recorded audio, and soft audio. But we tell, when training, we inform the network, this is model, this is soft. So we just condition with, for example, 1-0 if it's model, or 0-1 if it's soft. And then in synthesis, we can change this conditioning and do something in between, or something soft or something model.
Yeah, so I've understood this very well, and your example are to illustrate that there are unseen aspects that are.
Exactly.
But my question was about the database. If you want to synthesize something special, you need to think about the database.
Yes, of course. Yes. It doesn't generate something that cannot be generalized from the data that has been used in training. So you cannot ask for something that has never seen. For example, if you want to synthesize a phoneme but it doesn't appear in the data set, it's not able to do that, never. It really needs some coverage in order to generalize.
But here you show that for pitch, for instance.
Yes, for pitch and also for unseen phonetic context, because in this case of soft singing, there were in these 4-minute songs many phonetic combinations were not covered, so there were many unseen phonetic contexts asked to sing at synthesis.
So as your database is so important for the quality of your synthesis, how do you choose your database? How do you establish your database? Did you do these recordings, and did you?
Yes, I participated in that, but that's because of my relation with Vocalate, because this case of a Spanish female singer was for a vocalist voice. But in the case of Japanese female singer, we did not participate because this was developed by. But now we are planning in a couple of weeks, hopefully, to record a male English singer singing natural songs, and we hope to get a quality close to what we get in Japanese. But it's more challenging because English is phonetically it's much richer, and also pronunciation it's harder than Japanese. So we want to see what happens. And also we expect that the singer will not deviate so much from the score notes, because if he deviates a lot, then we will need to manually correct that, and that's can be overwhelming if it's not funded. So we'll see.
Hi. So I have a question about the core singing, because you it sounds very good, but you said there was something about the multi-speaker modeling, or so you generate each voice separately using the vocoder.
Yes.
Yes.
Yeah,
But
yes.
then how? So
Yeah, yeah,
what comes into the multi-singer model? How does it integrate in?
Yeah. So actually, it's very simple, because we have the 12 data sets, one per singer. We have 12 singers, and we train all together. So we have a single model, and the only thing we have to do is during training, where samples randomly selected from each of these data sets are used for computing an update and backpropagation and so on. What we have to do is to tell each of the samples some identification of which voice, which singer it belongs to. And for that, we just have to add to the control of the network, to the control input of the network, some encoding of the singer ID, which if it's 12 singers can be one hot encoding. So if it's the first singer, it's 1 and 11 zeros. If it's the last singer, 11 zeros, 1. And so we use that as the control input. The control input means that, sorry, go back. Yeah, control input is like that. So we add to the previous phoneme, parent phoneme, next phoneme, normalized phoneme position. We add here the singer again. Okay. So we concatenate such information, and that's provided at each time step of during training. And at synthesis, you have to provide the same information. But it allows you also to interpolate between singers.
So, but is it different from having a separate model for each singer to do the synthesis, except you have more data
it's different,
to cover
it's
more
much,
context?
It's more data, and if you do separately, you cannot interpolate.
In the core, you interpolate between singers, or you mean
We
you
did
can
not
have
do
a
that
in
for
between?
this demo, but you could.
Okay.
The same as for example, for for the case of the, for example, of the Spanish synthesis. Since it comes from 3 different pitches, we are interpolating the information at every step at synthesis. So there is an interpolation. But for timbre, not depending on pitch, but on a singer identity, you can do the same. You can interpolate also in the same way.
Again, what's the size of the pseudo database, pseudo singer database? How many songs inside? I remember.
Of the pseudo, I had here. It was for Spanish. It was for Spanish. It's 120 sentences per pitch, so 16 minutes per pitch.
For each pitch.
Yes, for each pitch. Yeah.
Okay, that's not much.
No, it's not much. For English, it's a bit more.
Okay, and I have another question. Does it fail sometimes? And if it
Fail?
does it fail sometimes?
Fail, yes,
Yeah.
of course.
When do you know?
When there is not sufficient coverage of some context, it fails. It doesn't generalize well. For example, I found that for some phoneme in the Japanese dataset, it only happened in one case and twice for another phoneme. And for those, it changed it sounds very different than the phoneme was intended, because they were so poor coverage.
So you mean what fails in this case is the modeling of the phoneme itself?
Yeah, it doesn't sound like the phoneme.
The timbre
you
modeling,
intend. Yeah,
spectrum.
But that's the reason. And then also when you generalize, for example, in power, or these cases where you only see one pitch and you want to generate at a different pitch, in some cases it might also produce some weird sound.
Okay.
So,
Because then one wonders why you don't use, if you use flat pitch for training, why don't you use just real speech then? Just
yeah, I could use real speech. Yeah.
Because you have lots of real speech then.
Yeah. But then the timbre qualities when you speak or when you sing, it's not the same.
Sure.
There's a difference. So it's rather, actually, the more suitable data set is actual singing.
I understand it's not the same, but if this makes you prevent, if this gives you information that you just don't have in the database, in the singing database,
you could
it's better than nothing.
You could combine, exactly. And actually you could combine a speech and singing together, and inform the system that this is a speech that is singing, and then it can generalize from speech what is not in singing, what is missing in singing.
Amazing.
Which is nice.
I'm afraid we have to stop here because we have to go eating. We have to be back here for Luc's defense. Thanks again, Jordi. Very impressive results.